Is a number of questions related to, broadly related to the formation of extrasolar planetary systems. So I'm going to begin with a little extended introduction about some problems of planet formation and what extrasolar planetary observations really tell about them. And the sort of the bottom line really is to ask how far can, if you like, an extended model of planet formation similar to that which was originally developed in the solar system take us in understanding different properties of extrasolar planetary systems. I'll then discuss some more technical work, actually the main work that we've been doing recently, which is really designed to look at the early stages of planet formation and what's going on in protoplanetary disks, in the gaseous component of protoplanetary disks, and how small dust particles, small solid particles, would respond to that turbulence. So that's going to be a fairly technical topic, and I'm just going to really emphasize some sort of qualitative results that I think are emerging from that maybe are quite interesting also in other accreting systems as well as in protoplanetary disks. And then I'll finish up with a few slides on some much more speculative work which we're really just embarking on, which is aimed to look at the question of where do the first large macroscopic bodies, planetesimals, form within disks. So this could work with a variety of collaborators. Much of what I'm going to be describing is work led by Jake Simon, who's a Sagan Fellow in Boulder, a student, Jacob Bruns, and Sean Raymond, who's now in France. So if we start with some observations, of course, the great advance in recent years is that we have much better observations both of the initial conditions for planet formation and of at least the statistical outcome of the planet formation process. So we have three distinct classes of systems that may be of interest. Gas-rich protoplanetary disks, which have maybe lifetimes of a few million years. So these would be rotationally supported structures, predominantly composed of gas, but with maybe 1% of solid material within them. Then later times, maybe tens of millions of years, though there's quite a range, we have debris disk systems. These are systems where there's a much smaller amount of gas, perhaps in some cases no gas at all. But we have solid material which is colliding together, producing dust particles which are eventually blown out or lost from the system. And then finally we have, of course, planetary systems, which in most cases, not quite all cases, but in most cases, are still being observed at very late times, billions of years after formation. So if we ask which parts of the planet formation process are directly accessible, if we think about the solid component of the disk, we would ultimately like to go from micron or submicron sized solids, which would be present in the interstellar medium and accumulated in the disk when the disk forms, all the way up to objects of tens of thousands of kilometers in size, representing terrestrial and giant planets. And of course, only a fairly small range of this size regime is directly accessible. So in both these gas-rich protoplanetary disks and these debris disks, we're mostly looking at rather small particles, maybe from micron sizes up to something like millimeter sizes. It becomes rather difficult to directly observe anything that's larger than that, centimeter or meter sizes. And then in planetary systems, maybe the smallest planets that are being observed are something like the size of Mercury. So we're going down, in some cases, a little bit below the size of the Earth and potentially habitable planets, but we're certainly not going down to anything in the hundreds of kilometer size regime. So there are large gaps in scale and in time here that are not directly observed, and some of those gaps are going to be very difficult to fill in observationally even in the foreseeable future. So we can ask a little bit then theoretically about what we expect to be going on as this size regime is traversed. So if we go from these micron sizes up to the sizes of gas giants, and it's really a story of competing roles of effects that are relevant, purely gravitational effects, and effects that involve the gas disk. So if we start with small sizes, so things you might sort of describe as colloquially as dust, so microns up to millimeter sizes, these are particles which, while the gas is present, have strong aerodynamic coupling to the gas. So they will be strongly affected by turbulence in the gas. They'll be colliding, and depending on what those collisions are like, they may lead to coagulation or they may lead to fragmentation. And what we know both from observations of disks and also from laboratory experiments is that in this size regime, coagulation is quite efficient. But we also know from observations that these very smallest particles survive in protoplanetary disks for many millions of years. So the basic story here is that in this small size regime, there's some kind of equilibrium set up between coagulation and fragmentation that maintains some kind of size distribution in this small particle regime. Then we go up to larger sizes, maybe sizes of tens of centimeters and meters. And then the dominant effect we think is taking place there is that there's rapid radial drift of these particles against the gas disk. And the physics here is very simple. The gas disk is partly supported by a pressure gradient, so it rotates slightly slower than the Keplerian velocity. The particles are trying to rotate at the Keplerian velocity, so they'll feel a headwind and tend to spiral in towards the star. And so one way or another, we require quite rapid growth through this sort of size regime in order to avoid really losing all of the solid material into the star. So that's a very simple effect, been known about for a very long time. This same size regime, for basically the same reasons, is also a regime where we can have interesting interactions between the solid component and the gas component if we can arrange a circumstance where locally the solid and the gas density is roughly comparable. And so these are new kinds of instabilities that are not present in either the gas or the solids alone. They're two-phase instabilities. The streaming instability is the important one here, discussed by Udin and Goodman now a decade ago. So here's a little simulation of that. This is a small patch of the disk. This would be the radial direction. This would be the vertical direction. You're looking here at the density of solids. You start with a uniform distribution of solids, and this instability leads to very rapid clumping in the solid distribution. So this may be important for forming larger objects, maybe other ways also of forming those larger objects. But one way or another, we come up to planetesimals, objects maybe between 1 kilometer in size and 100 kilometer in size, which are decoupled, largely decoupled aerodynamically from the gas disk. And then proceeding on, we have a phase where gravitational dynamics is expected to dominate. That's been studied for a long time. Various regimes of growth are known there. And then when we get larger again, we recover a coupling to the gas disk, but now not an aerodynamic coupling, but a gravitational coupling due to the excitation of various kinds of waves that a relatively massive planet will excite in the gas disk. So this is a migration and can lead to planets or planetary cores moving around substantially radially in the disk. And then finally, if we get up to maybe masses of 5 Earth masses or thereabouts, those are the kind of masses where we expect planets to start accreting gaseous envelopes and eventually give us something like the giant planets. So there's a fairly complex set of processes that are believed to be important here. A lot of them involve turbulence and aspects of the gas disk. So I'll be discussing later about why those are uncertain and what we can do to model them. But before doing that, I think it's worth noting that if we just sort of focus on this final stage of growth, the stage of growth that starts with planetesimals and maybe ends up at terrestrial planets or the cores of giant planets, there are models where dynamics, purely gravitational n-body dynamics, actually does a pretty good job of explaining some basic features of planetary systems that we see. And so one of those, which I'll just show in a moment, is the terrestrial planets in the solar system. Another is the excitation of giant exoplanets. We know many of the original extrasolar planetary systems discovered had quite eccentric orbits and quite inclined orbits in some cases with respect to the star, so they're dynamically much hotter than what we see in the solar system. And I'll also argue that this giant planet properties are sort of consistent with a continuum between a solar system-like and an exoplanet-like mode of giant planet formation. So let's first of all discuss the terrestrial planets. So this is a very simple calculation. What we've done here is just take a region of the inner disk, 1, 2, 3 AU here, and laid down a few Earth masses of relatively large bodies, here distributed in 500 equal mass objects, with some particular surface density profile away from the star. And we're going to ask how these objects evolve, assuming that when they physically collide, all collisions lead to perfect accretion. So on the lower panel here, you have eccentricity versus radius. And this upper panel is going to be a space-time diagram. This is a logarithmic scale in time, showing how objects grow together. So if you let this calculation go, it's a very simple calculation. You can do it on a laptop. You see these objects are excited from circular orbits. You can see some dynamical friction taking place there. And then as you see things grow, you can see things growing together, relatively speaking in place. So there's a little bit of wandering of this material radially, but basically material is growing in place. And here on a timescale of about 100 million years, you end up with 3 or 4 large objects, and at least in the inner part of this calculation, most of the smaller objects have already collided and been cleaned out. There's some remaining material out now where the asteroid belt would be. So this kind of model has been worked on in the solar system for a long time, and there are known problems with it. One problem that's often discussed is that the mass of Mars you predict from these kind of calculations is typically much larger than the mass of Mars that is really seen in the solar system. And that's just reflecting the fact that you would expect in most disk models there to be rather a large amount of material in the disk at the location where Mars eventually forms, and that's going to eventually form into a planet. But I would say, sort of at leading order, this actually gives a reasonable description of, let's say, the spacing of the terrestrial planets and their masses, with a fairly reasonable assumption for how much material would be in that region of the planetary system. So there's not much in the solar system terrestrial planets that really reflects anything other than the dynamics there, which is giving rise to a sort of marginally stable system as material is growing.
How does it depend on the surface density?
So if you had a higher surface density, you would end up with fewer but more massive planets, and vice versa. So that would basically be just a stability argument. Okay, now we can extend the same sorts of calculations to think about extrasolar planetary systems. And so here's a similar but slightly more involved calculation where we have a terrestrial planet forming material. We here have 3 giant planets, and here we have a massive Kuiper belt. So maybe 30 or 40 Earth masses of material, similar to what is inferred or suggested at least in models of the early solar system. And what we've done here is to take these giant planets and actually make them somewhat higher in mass than we have in the solar system. So you can see how this would evolve. And so here the colors in the inner part are reflecting the water fraction of the material. And initially, this terrestrial planet region grows very much like in the solar system. You can see things are growing larger here. We have some small bodies which are scattered to fairly high eccentricity. But then in a moment, we're going to have an instability among the giant planets. So we slow down the movie. Everything happens very quickly. And in a rather short period of time, we've ejected at least one of the giant planets, and we've cleared most of this material both from this primordial Kuiper belt-like structure and also from this inner terrestrial planet-forming region. So what you end up with in this specific calculation is one giant planet at fairly moderate radii, about 3.5 AU, and then one terrestrial planet which actually has a fair amount of water, but here has this very eccentric and very dynamically evolving orbit. Okay. So this is, of course, just one example. You have to do hundreds of these kinds of calculations to say something statistically about what would happen. Okay, but when you do that, what you find is that, at least as far as the giant planets go, the sort of dynamics that's shown there, so late-time gravitational instabilities among the planets, can do a reasonably good job at explaining sort of the basic features that we observe in extrasolar planetary systems. So here's one example. This is the eccentricity distribution of giant extrasolar planets seen with radial velocity. This is the cumulative distribution and the differential distribution. And this green curve here is the result of a very simple theoretical calculation where you just take 3 giant planets, you place them close enough down so that they will be unstable over a long time period and allow them to evolve under purely n-body dynamics. And it actually agrees quite well with an appropriately selected subset of radial velocity detected planets.
Is it fair to start from a situation when you already have fully grown giant planets and the inner part of the disk start from basically t = 0?
So it's an appropriate thing to do if you assume that the terrestrial planet region is like the solar system. So in the solar system, the final assembly of the terrestrial planets takes significantly longer than the gas disk lifetime. So in a solar system-like model, it's not such a bad thing to do. If you go beyond that, as I'll mention in a moment, it's a very bad thing to do, right? Because then it would not be correct. So you can model this, and you can also look at other properties such as the spacing of planets and the inclination of planets that are scattered into orbits that would encounter the star. And most of these properties actually agree reasonably well with what we see. So if you like, the giant planets, the giant extrasolar planets, quite a lot of what we see may be purely a dynamical effect, which could be explained if we make a few assumptions. that the giant planets arrive in these long-term unstable configurations when the gas disk is dispersed. It's not obvious why that should be the case, but we may assume perhaps that it is the case. As I was just mentioning, that the terrestrial planets form late, and then a connection between the extrasolar planets and the solar system can be made if we assume that there's damping from these small bodies out in the primordial Kuiper belt, and that damping is more important in the solar system, where the giant planets, are of relatively low mass, than in extrasolar planetary systems, where at least out on those large scales, we're generally talking about somewhat more massive giant planets. So that's what's shown in this plot at the bottom from work that did with Sean Raymond. This is the total mass of planets in planetary systems. This is the eccentricity of the planets that are surviving. When you have these outer debris disks that are relatively dynamically significant, when the planets are very massive, the disks don't make much difference to the dynamics. You basically just have pure scattering among the massive planets. You get very eccentric planetary systems. When you get into lower mass planets, but still in the giant planet regime, you get much more circular planetary systems. And the solar system would lie somewhere at the boundary of that transition. Now, obviously, this is not a unique dynamical model. There are other dynamics that is also very likely important in extrasolar planetary systems. But at least you can explain some of it based on these fairly simple considerations. Okay, so those are things that we perhaps can explain, but then there are other things that are clearly unexplained and which perhaps are at the heart of other mysteries in extrasolar planetary systems. For example, what's going on with the very close-in Kepler planetary systems. And these, I would say, are mostly connected with places, size regimes, where we expect to have a very rapid mobility of solids or planets within the disk. And there are two different places where that may take place. So one is at relatively small scales, between maybe millimeter sizes up to meters or tens of meters, where we have these aerodynamic effects which can lead to very rapid radial drift. So here, for some particular disk model, as a function of radius, is plotted drift timescales for objects of various sizes. This is millimeter sizes. This is 10 centimeter sizes. This is aerodynamic drift plotted here. And then you have some other curves here which describe the diffusive evolution of particles of similar sizes. And the point simply is that in the inner disk, here at 1 AU, these radial drift and diffusion timescales are really extremely short. So 10 to the 3 years, 10 to the 4 years, 10 to the 5 years. These are many orders of magnitude, or several orders of magnitude, shorter than the gas disk lifetime. So we would clearly expect that the precursors to the planetesimals would move very significantly radially before planetesimals are necessarily forming. So if you like, if you think about the solar system, we said we could do quite well in modeling the terrestrial planets if we assumed we'd managed to lay down a few Earth masses of planetesimals with some specified surface density distribution in the inner disk. But it's rather hard to see, or at least it's not explained easily, how those initial conditions come to be. Or at least we have to understand how this small material moves in order to understand that. Now then there's a second problem, which is maybe more directly connected to observations, which is that if we go to objects that are of Earth mass, if we look at this upper green curve, that's for Earth mass objects. This lower green curve is for 5 Earth mass objects. We can ask how rapidly those objects would move due to gravitational interactions with the gas. And again, we find that the timescales are very short. So if we're interested in the formation of the cores of the giant planets, so maybe out at 5 AU in the solar system at a few Earth masses, again, we're talking about timescales that are only of order 10 to the 5 years. If we go to the Kepler planetary systems, the super-Earths, the mini-Neptunes, and so forth, where we're maybe in at a tenth or a couple of tenths of an AU, then the timescales are even shorter. Even at an Earth mass, you're only at a few times 10 to the 4 years. So clearly, if we're interested in the formation of these close-in Kepler planetary systems, or how they would evolve over time, the interaction of those objects with the gas cannot be neglected really in any model. So in both of these size regimes, so in this small size regime, which is sort of the precursor to planetesimal formation, and then in this regime where we're thinking about forming super-Earths, perhaps close in, really it's the interaction between the gas, small solids, between the planets that is key, and we would really expect there to be very substantial radial migration of those objects, unless there's some particular location, perhaps, where that happens to vanish. Okay. So, and most of these things are not very well understood. Okay, so that was the introduction. I'd now like to say a little bit about protoplanetary disks, ultimately with the idea of getting an idea of what the background structure of these disks is like, so therefore how they would interact with these small solids, and then also what the turbulent properties are like, which will be important for the early stages of planet formation. So if we just start in general, there are sort of two sets of physical processes that will determine what the disk is looking like. One is the heating from the central star. So in most regions of protoplanetary disks, the thermal structure is largely determined by the heating from the central star. And then the other is how angular momentum is being transported or lost from the system. And typically we have sort of two separate models people think about for protoplanetary disks. One is to view protoplanetary disks as accretion disks, very similar to accretion disks in other systems, where the angular momentum is being redistributed by turbulence within the disk. And then, in a steady state at least, the surface density structure of the disk will be set by how efficient that turbulence is and how it varies radially within the flow. However, it's also possible to lose angular momentum in the form of disk winds, and if that's the dominant process controlling the angular momentum evolution of the system, that will tend to determine what the surface density and the radial velocity, say, in the flow is. So we're interested in turbulence for the purpose of understanding, if you like, the background structure of the disk. It's also clearly key to the particle dynamics in the regime where the particles are small enough that they remain largely aerodynamically coupled to the gas. So we'd like to understand, for example, what the role of turbulence is in setting collision velocities and determining whether objects coagulate or fragment at small scales. So if we think in general, there are a number of sources of turbulence that might be important in protoplanetary disks, which could feed on different instabilities or different sources of free energy in the system. So to start with, perhaps, if we think about early times, self-gravity may well be playing an important role. So when the disk is first formed, perhaps the disk has a large mass, maybe even comparable to the mass of the star, and so the self-gravity of the fluid itself will clearly not be negligible. So if we have early massive disks, we expect them to develop strong spiral arms, and both the accretion process and the turbulence on smaller scales will be dominated by that turbulent process. Now, if we consider later disks, the disk will be less massive, and we would perhaps not expect self-gravity to play a role. And there we have two independent sources of turbulence. So one possibility, which is the one I won't be discussing, is that there may be entropy gradients which are favorable to generating turbulence through effectively radial motions which are set up in the disk. So this is so-called baroclinic instabilities. Geoffroy Lézieux and Jean Papalouizou have discussed this a number of years ago. And if the conditions are right in the disk, and it's not at all clear that the conditions are right in most disks, these are instabilities that can set up vortex-like structures within the disk. So vortices are, of course, interesting because vortices are one way in which you can easily accumulate large amounts of solid material towards the core. So there's some extra interest in those instabilities for that reason. However, the other possibility, the one I'll be discussing, is Mhd instabilities. And these are essentially the magneto-rotational instability discussed by Balbus and Hawley now a couple of decades ago, which feed directly on the shear within the disk. So these, in their simplest form, are linear local instabilities with very rapid growth rates. So if you have differentially rotating disks threaded by magnetic fields, they're very inevitable instabilities that, in their nonlinear state, lead to turbulence. And these are the kind of calculations we've been doing. These are local calculations of these Mhd instabilities. This would be the radial coordinate, the azimuthal coordinate. This is the vertical coordinate. This is the disk midplane, and you're looking at a rendering of density here. And you here in an ideal Mhd calculation, so for a well-ionized disk, you just see this sustained turbulence, and in the midplane, you actually just see these waves bouncing around in the midplane. So in most accreting systems, so disks around black holes and other compact objects where the gas is well ionized, there's essentially no doubt that this is by far the leading candidate for what is going on to drive turbulence and angular momentum transport in those systems. So we'd like to understand how those same instabilities operate in the limit of protoplanetary disks. So, sort of alluded to there, there's some complexity and potentially some interaction between Mhd processes and thermal processes in the disk. So there's a number of areas of complexity. But we've been trying to focus on what I think is the first and maybe the simplest question, which is what is the outcome of the MRI, of the magnetorotational instability, in a fairly simple model where the disk is non-self-gravitating. The thermal physics is very simple. We actually just keep it to be isothermal. And the chemistry is also fixed. So there's no feedback from dust moving around in the disk and various other complexities that you could certainly imagine are present in real disk systems. Okay. So even if we consider that simplest situation, we still have a fair amount of complexity, which arises from the fact that in the induction equation, all three of the non-ideal MHD terms play a role in different places in the disk. So in general, we have the potential of ohmic diffusion, we have ambipolar diffusion, and we have the Hall effect, which all have different dependencies on what the magnetic field is like and what the ionization structure in the disk here is. And here's an illustration, an estimate of how those terms matter. So here you've got density over many orders of magnitude and temperature. And these different regimes here show different orderings of these non-ideal terms. So here, in this rightmost part, ohmic diffusion would be dominant, then the Hall effect, then ambipolar diffusion, and then differently in these different regimes. And if you consider the midplane of protoplanetary disks and the atmosphere of protoplanetary disks, as you can see, they track across these boundaries. Generally, as you go further away from the star, of course, ambipolar diffusion becomes more important because that depends very strongly on the density. But then there's a substantial difference between the midplane conditions and the lower density conditions, which would be present in the atmosphere. So there's complexity, and you really need to try to model the MHD, including all of these non-ideal effects. But the relatively new development over the last few years is that it is now possible to model each of these non-ideal effects at essentially the physical strength that we expect to be present in chemical models of protoplanetary disks. So at least in principle, it's a well-posed physical problem where we should be able to arrive at a converged answer that different groups using different codes can agree on. And various people, including several people here, Matt Kunz, Juning Bai, been working with Jim Stone, Geoffroy Lesure in Europe, Jake Simon, have been looking at implementing and testing these different terms. So I'll show some simulation results in a moment, but first of all, let me just outline the analytic expectation for what might happen, which dates back to work by Charles Gammie in the 90s, sometimes described as the dead zone model. And what Charles looked at was a very simple model where you just consider the ohmic diffusion and how that compares with this ideal MHD piece of the induction equation, which gives rise to the magnetorotational instability. So what you can do with a simple timescale analysis is to ask, if you had no non-ideal physics, how fast would the MRI grow? And the growth timescale is something like the scale we're interested in, which would be here the thickness of the disk, divided by the Alfvén speed, given some assumption about the magnetic field strength. And you can then compare that to the damping which would come to this ohmic resistivity, which is a diffusive process, which would be something like h squared over eta, where this is the resistivity. So if you just equate those two things together, you get a critical value of the resistivity, which depends on the magnetic Reynolds number, effectively, and that will give you a critical value of the resistivity below which, or above which, you would expect to damp MHD turbulence within the disk. And if you calculate what this resistivity would be for reasonable electron fractions, you find that away from the star, in the midplane of the disk at around 1 AU, you expect the resistivity to be high enough that it would be in the regime where it would damp the growth of the MRI. Okay? So qualitatively then, this is the sort of picture you would expect to produce here. If you're close to the star, the temperature is reasonably high. You have near ideal MHD conditions and quite vigorous turbulence within the disk. As you move further away, the upper layers of the disk are being ionized, perhaps by X-rays from the central star, from cosmic rays, from far ultraviolet photons. So these upper layers will be active, but in the midplane where you're shielded from those non-thermal sources of ionization, you expect the turbulence to be very strongly damped. And in the inner part of the disk, ohmic diffusion will be what is doing the damping. As you go further out, ambipolar diffusion will take over in that low density region and give you a rather similar structure. So this is a sort of theoretical idea for what we would expect the structure of the disk to be like in the planet-forming region. And there's additional interest in this because these kinds of structures are quite vulnerable to being unstable on long time scales. And so they may play a role in various outbursts of accretion onto the central star, which are often inferred observationally when we look at young stellar systems. So this is the cartoon picture. What I now want to show is some numerical results from more complicated models, more complete physical models, which include this full array of the non-ideal effects that are taking place. And I would say in general, qualitatively, they do support this kind of picture, which is based, as you could see, on quite simple sort of timescale arguments in the simplest case, but they also show some surprises. So the first surprise is that there's a very strong role, it appears, for net magnetic fields which would be inherited from the star formation process. So if we imagine the disk forming from the collapse of a molecular cloud, we would expect the disk initially to be threaded with some of that magnetic field which was originally present in the star-forming region. And even if that magnetic field is weak in the sense that it does not prevent the disk from forming in the first place, that magnetic field can still play a strong role in stimulating the MRI and giving us a different regime of turbulence. And that's what's shown here. So these are space-time diagrams of simulations. So time in orbits, this is height above the midplane, and the colors here are showing average values of the toroidal magnetic field in the simulations. So if you have very weak net magnetic field, so the disk is not threaded by very much vertical flux, then you have activity in the surface layers of the disk, that's a dynamo pattern of activity in the surface layers of the disk, but the midplane of the disk is rather dead, here due to damping by ambipolar diffusion. But then if you crank up the net magnetic field, you first of all get some activity taking place in the midplane, and then as you go to stronger magnetic fields, you get a qualitative change in the solution, and you end up with a solution which, just in this variable at least, doesn't really appear to be turbulent at all. We just have a different sign of magnetic field above and below the midplane. Okay? And the striking thing is that this kind of transition occurs for magnetic fields that are really quite weak. So if we measure them in terms of the ratio of the gas pressure to the magnetic pressure in this vertical field component, this middle panel here is a beta value of 10 to the 4. So by no means is this the sort of strong magnetic field that people discuss, for example, when they're thinking about classical models for protoplanetary disk winds. So it suggests that there's this memory of the magnetic field which is inherited from the star formation process that would play a very substantial role later in how the disk behaves.
So in the top panel, do you actually get an MRI going at all? Or is it just a differential rotation that stretches the field in this way?
I'll show that in the next slide. Here we are. So yes, so in that top panel, we're really not looking at a turbulent structure at all. So here, this is that top panel, and this is that middle panel. These are now renderings of the magnetic field structure within the disk. And so in that middle panel, you have this tangled structure of magnetic fields, which would be characteristic of MRI-like turbulence. And then when you go to that somewhat stronger net vertical field, you have this much more organized pattern of magnetic field lines, which at least naively, you might say is more like what you would expect for a wind solution from the disk. Okay. So what appears to happen here is that there's this transition from a sort of turbulent structure to a disk wind-like structure as the net field increases, and that transition, at least in these local simulations, occurs for quite weak vertical fields that are threading the disk. Now, there's some caveats about this which are important to note. These are local calculations, and so they're very ill-suited to saying anything quantitative about disk winds, which are obviously large-scale flows which eventually have to connect to infinity away from the disk. But nonetheless, this is actually a fairly generic result. In ideal MHD, this was discussed as long ago as 2009 by Suzuki and Inotsuka, and then in the non-ideal context, a large number of papers in the last few years see very similar sorts of structures. So what this may be saying is that the dichotomy between turbulent-driven disks and disk wind-driven disks is somewhat misleading. In reality, if we have turbulent disks that have even quite weak threading fields, at least some of the angular momentum evolution in those systems will be driven by material which is flowing away along magnetic field lines from the disk. Let me then just finish up by saying something about the Hall effect. So I haven't mentioned anything yet about the Hall effect, and the Hall effect is notable among these non-ideal terms in that its effect on the dynamics depends on this omega dot B. So it depends not just on the strength of the magnetic field, but also on how the magnetic field is oriented relative to the rotation axis of the disk. So a vertical field that is in the same sense as the disk rotation has a different effect on the dynamics from a vertical field that is opposite to the rotation. And in general, an aligned net field promotes accretion, leads to greater turbulence in the disk, and an anti-aligned field quenches accretion. So we've done a much smaller number of simulations on this particular topic, but here's a few examples. So this is radius here, and this is the efficiency of turbulent transport measured in terms of the Shikura-Sunyaev alpha. And if you just concentrate on these black triangles, these are simulations that have a particular value of beta for the net field of 10 to the 5. And in these simulations, as you go from the outer disk, where ambipolar diffusion is dominant, toward the inner disk, where the Hall effect plays a large role, you get a quite marked increase in the turbulent stress as you go further in, or at least in the accretion stress. Now, if on the other hand you take an anti-aligned field, we only have a couple of simulation points here at the moment, but you can see in the outer disk you get relatively similar values of the turbulent strength, reflecting the fact that ambipolar diffusion is just dominant there and damping the accretion. But when you go into much smaller scales, you get maybe 2 orders of magnitude difference in the strength of transport when you simply reverse the sign of the field. So these are topics which we're still working on, but clearly the expectation here would be that if you imagine the fields are randomly distributed when the disks form, then the outer disks might be quite similar, regardless of what the sign of the magnetic field is. But as you go into the inner disk, you could have a quite bimodal structure of the accretion flow. In one case, you have rapid inflow and low surface densities. In the other case, much suppressed inflow and much higher surface densities. So it's interesting to ask observationally whether there's any evidence for that kind of bimodality, which would be coming ultimately from this Hall Mhd physics. So we're interested in trying to test these models observationally, and just want to mention a couple of ways that perhaps could be done. So one possibility is that some of these MHD turbulent processes result in large-scale structures forming within the turbulence, which in principle could be directly observed in images of protoplanetary disks. So these are the so-called zonal flows. So these are, again, space-time diagrams, except here this is now the radial coordinate. This is time. And the colors here are representing over and under densities in the surface density of the disk. So on timescales of a few hundred orbits, the MHD processes within the disk collect themselves into regions of overdensity and neighboring regions of underdensity, which are in balance, where this pressure gradient that's being set up is being balanced by variations in the azimuthal velocity within the disk. So these would be ring-like structures. So these are local simulations. In a more complete model, these would be axisymmetric ring-like structures which would develop spontaneously out of the turbulence. Many of you may have seen this recent ALMA press release image. I believe the data for this was released today. HL Tau, relatively young disk, which seems to show these very, indeed, prominent rings in the distribution of a millimeter continuum from the disk. So this might be a large-scale features that we could observe. We may also be able to observe the small-scale turbulence from the broadening of molecular lines which are produced either in the disk atmosphere or towards the disk interior. And this is something we've been looking at in some detail with observational collaborators led by Meredith Hughes. These MHD models make quite distinctive predictions for what the turbulent velocity should be as a function of height above the midplane. Typically, near the midplane, you have these damping or dead zones with rather low levels of turbulence, and then you have much higher levels of turbulence approaching transonic speeds when you reach the disk atmosphere. So if you observe in the disk atmosphere, perhaps with a quite optically thick CO line, you would expect to see high velocities. If you observe closer to the disk midplane, perhaps with an isotopolog of CO, you would expect to observe much lower velocities. We've been making predictions here in channel maps for CO3 to 2, for example, for what you should see based on these MHD calculations. And we have some ALMA data from cycle 2, which hopefully will test that. This is indicating the region where the ionization is low. So the upper regions here are where FUV photons are providing some ionization of carbon and oxygen. Okay, so let me now finish off with a few minutes discussion of this more speculative topic of where planetesimals form. And the basic point I want to get across here is that in many models for planetesimal formation, the conditions under which planetesimals form are quite restricted. They're quite restrictive of the conditions in the disk. And so, for example, in this streaming instability type model, which is perhaps the most plausible way of forming planetesimals, you need two things to be simultaneously true. You need moderately large precursor particles, such that their stopping time in dimensionless units is something like 10 to the minus 2 or larger. And then typically you also need a local enrichment of solids compared to what the mean value would be in the disk. So you need these things to be locally true in order to trigger this very rapid dynamical timescale concentration of particles. Now clearly, particularly if you need this local enrichment of solids compared to the mean disk value, it's very hard to satisfy that everywhere in the disk. If you're concentrating solids in some places, you are deconcentrating them in other places within the disk. So if this is how planetesimals are forming, the expectation would be that planetesimal formation would be concentrated in regions where perhaps the radial drift and the concentration processes are favorable for attaining these conditions. So where would that be? Well, if we think about these MHD models for disks, one place where that might happen would be at the inner edge of this dead zone relatively near to the star. So what's going on here is that if we're very close to the star, the disk is quite turbulent because it's relatively well ionized. If we go just outside the region where the alkali metals are ionized, we expect the levels of turbulence to be much lower, and so gas will pile up at that location before it flows in more rapidly as it crosses that inner edge of the dead zone. So this would occur at the place in the disk where the temperature is maybe 800 K or 1000 K, and lead to a local pressure maximum, which would tend to concentrate these moderately aerodynamically coupled particles in that point. And you can do some quite simple models of that, placing particle traps at this radius, and for reasonably sized particles, so the red curves here are for 1 centimeter, at a few tenths of an AU, you could easily get a concentration of an order of magnitude or so in the local density of particles at that inner dead zone edge. Now there's then a separate piece of physics further out at the snow line, which is actually discussed much longer ago. If we consider the water snow line and imagine icy particles drifting radially across that location, they will sublimate inside the snow line and setting up a gradient in the concentration of vapor, which will then tend to be diffusing out across the snow line and recondensing into solids. So if you do models for that kind of process, you find that again, for millimeter to centimeter sized particles, you get a substantial enhancement of the solid density just outside the location of the snow line. So this is physics that was discussed by Stevenson and Lunine. It's also possible that this could combine with these MHD processes, and those are some models that were discussed by Kretke and Lin. So if we imagine that radial drift is taking place everywhere, bringing a large amount of material in from a reservoir further out, I would say it's this location, the snow line, this inner edge of the dead zone. These are the place where there's physical structures in the disk which would be very preferential for forming planetesimals. So we can ask what would happen later to terrestrial planet formation if we assume that that is in fact the only location where planetesimals are forming. So we've done some toy calculations of that kind, where we assume that planetary embryos form in these locations at a rate which is set by the radial drift of these small precursor solids. And of course, this snow line, this inner edge of the dead zone, it's not an absolutely fixed location in the disk. It's fixed on short time scales, but on long time scales it will move around as the temperature in the disk evolves. Generally, those locations, those trapping locations, will move inwards as the disk becomes cooler. So we've done some very simple calculations of this. It's quite similar to those terrestrial planet formation calculations I showed before. They're done with mercury, perfect accretion. There's no pebbles or small material which interacts dynamically with the forming objects, and there's no type 1 migration with the gas. And we're considering typically drift fluxes of the order of tens of Earth masses per year of solid material encountering these trapping locations. So what do we get there? Well, we get basically pretty much what you might expect from quite elementary dynamical considerations. If we imagine we're at the inner dead zone edge, so at radii of a tenth or a few tenths of an AU, and we start with one of these trapping zones and it moves inwards over time, as material is building up there and growing into larger objects, we have a sort of sequential model of planet formation where you start by forming planetary objects, the outer part of that region, and then as time goes on, you stop feeding this outer object and you start forming a new one, and so on and so forth. Okay? So the growth occurs sort of sequentially outside in, and because you're so close to the star and the masses are not that high, there's really very limited scattering of that material to other places within the disk. So again, it's an in situ model for how objects are forming. And the radial extent of the planetary system you form there is just set by the amount of change in disk temperature that takes place, and typically it's a factor of a few for reasonable assumptions about how the heating of the disk by irradiation and viscous heating would work. What sort of planetary systems do you end up with there? Well, of course, it's very much like any other in situ model for these close-in planetary systems. So the dynamics is very similar. There are small differences in, for example, the eccentricity or the angular momentum deficit of the systems you form, but in reality, those would be completely wiped out by the subsequent effects of migration. So this could be a way physically to take the large amounts of material that are in the outer disk, move them to the inner disk by radial drift. This is where they would preferentially form planetesimals and subsequently grow up into planetary embryos and Kepler planets. Now, we've also looked at the same process at the water snow line, so out at maybe 2-3 AU, and there the situation is a little bit different because once we get objects of a few Earth masses, those can scatter other objects quite substantially radially through the disk. So what we find here is that there's a strong scattering. Here you can see a bunch of systems formed in this way, and you can see these scattered objects relatively far away from where they started within the disk. And here in this picture, it's somewhat easier to obtain large core masses that might be suitable for subsequently accreting gas, primarily because the accretion is all taking place at the very inner edge of where most people consider giant planet formation to take place. So giant planet formation in general gets much harder as a very steep function as you move to greater distances from the star. So if you force everything to really be taking place at the water snow line, you're making things as easy as you possibly could. And as in the case of the Kepler planets, of course, these cores would be expected to migrate, not only in this model where you're forming things at snow lines, but actually in any model where you're growing up to have large enough objects that could subsequently accrete gaseous envelopes. So what I would argue here is that the progenitors actually have quite a large number of the observed planets, both the close-in Kepler planets and the gas giants we see further out, in principle, at least based on these sort of dynamical considerations, could really be actually forming at quite a small number of discrete disk locations where the conditions are favorable. Okay, so I think I'll just put up the summary there and take any questions.